So our big safety concerns for the lab today are that let's talk about what we have. We set up the plate, the Petri dish with agarose gel, as we discussed yesterday. The pH of the agarose is greater than 7. We use sodium hydroxide in the mix to make the pH greater than 7. There's an indicator in there called phenolphthalein. Phenolphthalein is pink when the pH is greater than 7. So you're going to see this is pink. Oops. This is pink, or it should be. So the Petri dish should be pink, and the agarose gel, the gel itself should be pink. So, James, could you do me a favor and close the door, will you? So, your job, you should know that the phenolphthalein is a poison. Specifically, it will give you bad diarrhea. So make sure you don't lick it or drink it or eat it. Make sure you're wearing gloves. It is not really that dangerous in the gel, assuming you are not, as I said, eating it. And I think it's funny, like someone's going to eat it, but if you're talking a lot, you're playing around, and a piece of that gel goes flying in your mouth, it's in your mouth. You've just pretty much eaten it. So best thing is not to be very careful when you're working with this. So that is a danger you need to be aware of. So we're talking about safety right now. The other couple things you have to be aware of is that you have sodium hydroxide. That's a strong base. That's in the gel. Now, it won't hurt your skin if you touch it for a second, or if it touches your skin and gets on. It's in a gel, so it's not really that dangerous. However, if it gets on your skin, just wash your hands. Wash your hands with water. Just rinse it off. Sodium hydroxide. I would use soap and water because you want to get there's poison in the gel as well. As I said, phenolphthalein is not something you want to be drinking. You're going to have a beaker, a small beaker, but a beaker nonetheless. To remind you, a beaker is a cylinder. You have a beaker of acid, hydrochloric acid. And the hydrochloric acid, although a low concentration, is still a strong acid. And that's at point, it's at a, see what was it now? Yeah, 0.2 molar, where the base was 0.1 molar. All right. So those are the real safety. Oh, and maybe the knife. You have to be careful not to cut yourself. You have to be careful when you're transporting a knife. It's pointed downwards, that kind of thing. All right, so that's the safety concerns. The setup is you're going to have 3 large cubes. All right, 3 cubes. One's going to be large. Unfortunately, the mistake I made, because I used Petri dishes, the depth for all of them is equal to 1 centimeter. So that means that no matter how you cut it, the surface to volume ratio is going to be the same. So that's a problem. But we can still do it, and I think you'll still learn a lot about how this works. In fact, I was going to ask James to do another one for tomorrow with varying depth, and we'll record it, and you can see what it's like, the difference from the data on Monday when we go over it in class. So you have a length. Your large block will be something like, definitely it'll be 1 centimeter deep, plus whatever centimeters wide, plus whatever centimeters long, and then the medium one, obviously there's still 1 centimeter deep, plus, or by whatever. Now what I put is 3 centimeters by 3 centimeters is what I put on the board. 2 centimeters by 2 centimeters. You can follow that or you can change it. You have a Petri dish worth of gel to work with. So cut out a square at whatever sizes you think is reasonable. I thought it was very smart when I told James to pour them into Petri dishes. Unfortunately, it limited our results, but that's fine. I didn't really think it through. It's a problem with the procedure, something you might want to enter in your error analysis as far as trying to see what we see. So one, with the experimental design, had a flaw, and that flaw is that the depth was the same for all, depth the same. You'll see when you do your calculations that your surface area to volume ratios are all going to be the same. So you have a hypothesis, it's written up there. You're going to write your own hypothesis for your lab report, whatever that is. Your hypothesis, the larger the surface area to volume ratio, the blank time it will take for the color change to happen. Now, there was a mistake in experimental design, as we said, so that's going to impact your ability to answer this hypothesis. Interestingly, a ninth grader thought about something. He did his homework, the same homework you had, which was how do you increase surface area to volume ratio? And he knew that in the body, we fold, you increase folding. And in fact, during the brainstormers session, one of the ninth graders asked the doctor, the physician, that question, or her homework question, to verify her answer. And the doctor talked about the folds in the brain and the folds in the gut as examples of folding in biological systems to increase surface area to volume ratios. And when he was pulling out his gel cube, his square, you're going to take your Petri dish, you're going to measure, you're going to cut out with a knife a square. There's going to be a certain depth. And to do that, you cut it, and then you kind of have to scoop it out. He was trying to scoop it out, and what happened was his teared. So there's a tear in the gel. It stuck together, but it was a tear. And he asked himself, is that going to make a difference? The fact that I have this square that's torn, it didn't lose any material. It just ripped, if that makes sense. So it just ripped open. Would that make a difference?
Well, it isn't folding, so I'd say no.
Like, do you have any more surface area if you didn't? So it just ripped. Is there any more surface area here in this area? Did this add surface area?
No.
So if I measured the length from here, if I had the same square, same depth, right? Same thing. I don't know how to do this, but there you go. I don't know, that doesn't make sense. So same depth, right? You agree?
No.
So is this more surface area? Well, let's make a measurement. Let's say this is 1 centimeter from there to there. So say that's 1 centimeter from there to there. Let's follow it. If this is this, it goes this way. You have to go down. If you're a person walking along the edge of this, you walk across, you walk down, you have to keep walking all the way around this way. Is that more or less than 1 centimeter? Look, watch the arrow. Are you watching the arrow? Let's watch it. It's going across. I have to follow it, follow it, follow it, follow it, follow it, follow it. Is that more? Is that longer? Yeah. So that impacts surface area, doesn't it? Because still 1 inch, it's still 1 centimeter deep, but this is longer than 1 centimeter. So which one's going to be longer? This one, the one that has, in essence, the rip actually turned out to be a fold, very similar to a fold. The impact is the same. Does that make sense? It's confusing, isn't it? Okay, so.
I get it. It's just like, I thought you were pushing them together.
Right, like you have it embedded in the beaker, and the acid can get in here, in this space, where here, this cube, the acid only has this space to get into. But here, the acid has all this space to get into. Isn't that more than this? Yes or no? Follow my arrow. Are you ready? Are you following my arrow? All right, look at it. Let's look at it. I go from here to here. That's a centimeter. From here to here is a centimeter. Now, you don't see that this is longer? If I'm walking, if you had to walk this, which would you rather walk? From here to here, or from here to here? You're right, it's one thing, but isn't there more area to cover? Isn't it the distance longer? Is the distance longer, yes or no? No, don't guess. Look at it. And if you don't see it, say it.
I see it, but it doesn't.
Okay, what doesn't it make sense? All right, come here. Well, come here.
Use this.
No, come here. I'm going to show you. Come here. Stand over here. Stand right here. Come on. We don't have that much time. Just stand right here. Look. Stand right here. Walk from here to that corner. All right. Now, I want you to walk down there, all the way there, walk back, then walk back to here. Go ahead.
I get what you're
No,
saying.
go ahead, keep walking. Which one is longer?
That way.
Okay, so you had to travel. Now, you're asking how to make a difference. If this were a cell, and this was one side of the cell, if you rip the cell, but you don't remove any of the contents, right? It's still the same volume, but you're opening it up. So there's more area for liquid to enter. Does that make sense? So, I don't have a... Here.
Use this box.
All right, I'll use this box. Here, give it to me. So this box, right now, this is the only area you have for the acid to get into, right? But what if I ripped it? Just ripped it open. Just kind of separated it.
Like for the cell?
Like if I rip the agarose gel, it's ripped open. Isn't there more area for the acid to get into? This whole area is the acid can get in there. Now remember, this is not a box. This is a gel. So it's all one container. Isn't there more area for it to get into here, here, instead of 1, 2, 3, 4, 5, 6 sides? It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sides.
I was getting it before now.
This is 6 sides, correct? If acid's going to get in here, imagine it's an agarose gel. It's a little square, a little cube. All right? How many sides can the acid get into this square? 1, 2, 3, 4, 5, 6. 6 sides. The sum of the area of those 6 sides is the surface area of this cube, right? If I rip it open, how much do I have more area for it? I have more surface area. More surface area because it's open. The volume's still the same. See, the volume didn't change, but the surface area increased. So by accident, actually a 9th grader thought of this, and I was stunned that he thought of that. And he came to me and said, didn't this increase? He said, yeah. So I asked him, what did you get? Because this was after the experiment was done. Was the time shorter? Because this surface area to volume ratio was larger for the ribbed one than it was for the one that wasn't ribbed. Does that make sense? So I asked him, did he get a shorter time? He did. So it was really stunning that that accident actually saved the lab and we were able to make sense of it. So here's what I want you to do. I want you to create these three, and I want you to create one and then make a little cut in it. Don't get rid of any of it, right? But keep, because if you get rid of a piece, then you're reducing the volume. So that messes up the experiment. So cut it, make a little zigzag like that in one of them, in one of your extra pieces. So you're doing 4 instead of 3, right? And see if the increased surface area actually does increase or decrease the time necessary to get the color change. Does that make sense? So this is a way to actually answer your hypothesis with this kind of flawed experimental design. All right. So you have three sizes. You have a large, you have a medium, you have a small.
What size do you want the one to be tiered?
But it's whichever one you want. I would get another one. Let's say large 2. If I kid, you have to be careful because you only have one petri dish. So you can large A, and then you have large B. Large B could be tiered. Does that make sense? So you're going to take your petri dish and you're going to cut out a 3 by 3 centimeter, a 2 by 2. It's just an example. I don't know what sizes you feel comfortable with. From my experience this morning, the 9th graders were able to cut out plenty. There was plenty of space. They do even a 4 by 4. But whatever, 3 by 3, 2 by 2, and a 1 by 1. You can, obviously, I said centimeter, and maybe do another one that's a 3 by 3, so 2 3 by 3s, A and B. And B, you tear. You cut open, in a zigzag pattern. So in any case, you have a large, medium, and small, and a second large, and you're going to have this in a table. Large, A, large, or rather, large, A, large, medium, small, and large B. Then what you're gonna do, as I said, it's on the board already. It's still on the board from this morning. You're gonna take and you're gonna calculate the surface area. That's length times width. Length times width. And so length times width times 6, right? You're probably not going to be, in fact, I'm going to tell you right now, do not try to calculate this. This is not going to be calculated. You just know it's more than the large A.
Do you want us to do the same size as we did for the large?
Yeah, so these A and B are going to be the same dimensions. It's just you're going to crack it open.
So can we write something like, let's say X is greater than whatever the...
Yeah, you can do that. Yes, you can. Surface area is larger. I just put surface area larger. Okay, volume's the same, surface area is larger. So surface area to surface area to volumes can be larger. Does that make sense? In fact, what you can do is instead of numbers, all right, so we can just say volume, and you can do length times width. Let's do 1 centimeter, rather not 1, it's 3 centimeter by 3 centimeter, so that's 9. Do the math with me here. I'm doing it for you. 3 by 3 is 9, times 6 is 54. So that's my surface area. This is my surface area for the large. The volume is going to be 3 by 3 by 1, so that's 9. So what's 54 divided by 9?
6.
is 6. And the surface area to volume ratio is going to be 6 all the way down, because no matter what, it's going to be 6. So let's do the medium, for example. The medium is 2 times 2, which is, 2 times 2, which is 4, times 6 is what?
4.
What is it?
24.
24. So the volume is 2 by 2 by 1, which is 4. So what is 24 divided by 4? All right. So you see how the surface area to volume. That's why I messed up when I told James to put them in petri dishes, because I kept, by accident, I kept the depth the same. I didn't think about it. So 1 by 1 is 1 times 6 is 6. And then, so the volume is 1 by 1 by 1, which is 1.
So do we just want to write in the 6s right now?
This is all done. I'm doing the math for you. Everything's done. That whole table's done. Well, most of it. Here, the volume is still going to be the same. It's going to be 9, because it's still going to be 3 by 3 by 1, right? The volume is still 9. Same volume. Do you see that? The volume is still 9, because it's the same as A. The difference is B, the surface area is larger. I don't know what it is, and it's hard. I don't want you to try to calculate it. But the surface area to volume ratio, then, if it's larger and the volume's still same, then the entire surface area to volume ratio is going to be larger than A, right? Or larger than 6. How's that? That's probably better than to say. I like that. Whoever said 6 was a good idea. Larger than 6. So it's definitely larger than 6. So
If we write x is greater than 54 and x is greater than 6, we use the numbers.
say that again.
X is greater than 54 for the surface value.
Yeah, that's good. I like that.
Surface value over volume, x is greater than 6.
Yeah. Right, I would use a different one for the, if you're using surface area as X, then I would use Y for surface area or whatever. But yeah, that's good. So then you're going to measure time for every one of these. You're measuring time in seconds. That's it. And so you're going to take your cubes, your 3 cubes, your large, your medium, your small, and then your large rip version. You can drop them in there and see what happens. All right. Now, some groups put them all in one at a time and waited and watched. Some groups put all of them in, and then they waited until every time one became clear, they wrote down the time for that one. What you'd expect to see is what? What would you expect to see? If our hypothesis, you know what? That's for you to figure out. You have to write that up. So what did you expect to see? That's your hypothesis. Whether you expect to see the time to be shorter with a larger surface area to volume ratio, or longer, or the same, then you have to ask. Make sure you have the hypothesis written down before you move forward. Now, once you've measured the time, how are you going to graph it? You have to graph it. How are you graphing it? You're using, when you're comparing numbers, hear this clearly. When you're comparing single values, when time is not changing repeatedly for each sample, you only have one number for each, right? The large, the medium, large A, medium, small, and large B is all going to have one time, not multiple times, right? It's only going to be one time span in seconds. Is that correct? You can't do a scatter plot. We discussed this yesterday. You have to only do a bar graph. It's really the best way to do it. So the question is on the X, Your dependent variable is time, and your independent variable is surface area to volume ratio, and or maybe it's sample. Maybe, you know what, because they're all the surface area volume ratios are the same, you just say small, medium, large, A, and large, B, and then you put your bars. Whatever it's going to be, whatever it turns out to be, put your bars for each one. And that's it. That you're going to write up, come to a conclusion as to why your results, did your results match your hypothesis, why or why not, what are any of the errors, make sure you're paying attention, you're describing it. I told the ninth, they're mostly ninth grade in my first period to take pictures. They took pictures using their phones. And they're going to incorporate it. They're going to use Microsoft Word and Microsoft Office to incorporate the pictures into their documents. And I think they're ready to go. I hope they're ready to go, and the same is going to be for you. Yeah. Except I expect a better and more descriptive explanation for all your work, because you're seniors and juniors, so I expect a more eloquent discussion. All right, goggles and gloves. I have the acid. Beakers are in the back. There's some beakers in here. Rinse them out. After you have your gloves on, rinse out your beakers here in this sink. The knives are in there as well, so rinse those off. Please be careful with the knives. They are sharp. And we have the Petri dishes with the agarose and the phenolphthalein. If I have no questions, I'm done talking. Any questions? All right, good luck. I will be grading for accuracy. I expect to see results that make sense. If the results don't make sense and you have no explanation for them, you failed the lab. All right, so pay attention. So when we're talking about the lab report, we have to consider that you want a section that says introduction, where you are thinking about, what is the definition of osmosis? How is it that the phenolphthalein, the indicator, let's just say indicator, is working in the lab? You might want to talk about how the experimental procedure was flawed because the teacher kept this depth the same, and how the rip in this case of the gel increased the surface area. So then you would want to have a hypothesis after you've introduced your material. And in your hypothesis, you want to describe, well, if the surface area to volume ratio is larger than what did you expect? Was that right? What did you expect? So, is the time going to be shorter? Is the time going to be longer? Will it take longer for osmosis to happen or shorter than osmosis to happen? Remembering that how are you measuring if osmosis is happening is the color change. The color change and how fast it happens. Remembering that the indicators that letting you know that the acid where you put the gel into is flowing, right? That water is acidic. that acidic water is gonna osmose or diffuse into the gel at different rates depending on the surface area to volume ratio. All right. So then you have your chart. You have your data. You should have, first of all, your materials and methods. You have your materials and methods where you list your materials, your safety concerns. So safety concerns, your materials, and your procedure. What did you do? And then once you're done with materials and methods, you're going to have your results. And the results are going to be your data. That's your data table that you saw on the previous slides. Rewind it if you missed it. You should have written down. I actually went through all the numbers and created the numbers for you. Then you have your in the results section, or let's put it in the analysis. You're going to have a graph. You're going to have your graph, and remembering that you're putting your independent variable here, your dependent variable here. Your dependent variable is the time in this case, because that's going to depend on the surface area to volume ratio. The best way to graph it, as I said earlier, is I think the best way to graph it, which I've obviously been wrong more than once this week, but what I believe the easiest way to graph is to say small, medium, large, then large A, and then large with a rip. So same dimensions except it's rip. So by definition, it has more surface area. And then this is still time in seconds. And you're going to have different bars. And theoretically, these three should have the same bars, the same time, because they have the same surface area to volume ratio. If surface area to volume ratio has any impact on how fast osmosis happens, then these three bars should be the same. Then the lower bar, the larger bar with the rip, should be a shorter time because it has more surface area, same volume. So, okay, that would be the analysis. That would be this is, by the way, the answer to your hypothesis, the answer to the relationship between surface area and volume and osmosis rate. And then your conclusion. Your conclusion should answer the question, did the results support or disagree with your hypothesis? That's the question. And then why? Don't forget, you want to describe it in terms of osmosis and surface area and volume ratio. Don't forget that when you're coming up with your conclusions, you should have a section of your conclusion that talks about your errors and how you corrected them or took them into account when you did your analysis or came to your conclusion. And there were errors. There was an experimental design error for one, and there were other errors as we went on. So errors, obviously, why did the reasoning? How are you going to be judged on your conclusion? Is it logical? Are your statements supported by evidence? I'm looking for evidence from the lab. I'm looking for your logic, your evidence. I'm looking for you not contradicting yourself. So stay consistent in your discussion. All right. And also you should have, when you're looking at describing the materials and methods, describing your methods, adding the pictures that you took in class. If you have a video, if you took video, then maybe you do a QR code.
Yeah, start with small.
So you can add a QR code
Small and then the size.
link to your YouTube video. You can create a YouTube video and upload it. And then you have this QR code number, right? Or not really number, but QR code that you add to your report and or the HTTP site, right? That has the reference to the video so people can actually see what you did. All right. Well, that's it. I'm going to give you, I thought better on it. Weekend is not enough time. I'm going to give you not to this Monday coming up, but the following Monday for you to turn in. That gives you Thursday to come and ask me questions. All right. Have a good one.